Okay, ladies and gentlemen, we are now in chapter 6, and this is called the normal distribution. And we'll see here in just a few moments what the normal distribution is all about. So this video is chapter 6, recording number 1. I want to talk first of all, as always, I strongly urge you to read the outline, get an idea of where you are, read the objectives, and as you're going through the text, you'll see the objectives are noted on the side of the page so that you can kind of follow along and see what objective you're at or what objective is being discussed. So for example, objective number 1 is identify the properties of a normal distribution. You'll see right here, that's in section 6.1, page 313 is where the author discusses that. So it's very useful, in my view, to look at the objectives. It gives you an overview of what to expect. All right, so we're in chapter 6 now, as I said, so I am going to refrain from reading quite as much as I have in the past. I'm going to start just saying, you need to read this on your own. I'll do my best to help you understand things, but ultimately you do need to start getting independent on this. Okay, so here's the objectives. This is what we're going to be talking about. Okay. I would say the most important issues here, the most important objectives that we have is this area here, talking about the probabilities of a normally distributed variable by transforming it into a standard normal variable. So remember, I have not talked about this before, but there's a concept called a mapping. You go from one variable to another variable. We typically will refer to that as a mapping. So what he's saying here is that we're going to take some variable and we're going to transform it into what is called a standard normal variable, and it's for convenience. That seems to be the hardest thing for people to get their arms around, so I will spend some time on that. Then the central limit theorem, that's a very important concept for us. Okay, so he talks here about what is normal. Why do we call it normal? There's different names for it. Sometimes we'll call it a normal distribution. Other times, other authors will call it a Gaussian distribution. Gaussian is named after Gauss, a very famous mathematician. It's G-A-U-S-S, Gauss, or Gaussian is G-A-U-S-S-I-A-N. Another common expression is you call it a call it a bell-shaped curve, a bell-shaped distribution. I would say normal distribution is pretty much the most common expression, a normal distribution. Okay, so read the objectives, please. Okay. I guess the first thing that we need to make sure we understand is that this is chapter 6, and we're talking about the normal distribution. This relates only to continuous variables. Now, it's a little tiny bit unfortunate that the author didn't put that in the chapter title. Chapter 5 was discrete probability distributions. Chapter 6 is continuous probability distributions, and specifically we're going to talk about the normal distribution, because the normal distribution is the most important continuous probability distribution. I wish he would have said that so that we would have made it abundantly clear that we're going from chapter 5, discrete probability distribution. Chapter 6 is continuous probability distribution. In any event, he's talking about how the random variables can be either discrete or continuous. And we discussed previously what discrete means. Okay, it cannot assume all values between any two given values of the variables. So classic example would be how many baskets did the team score? You scored 6 baskets or 6 points, or you scored 7 points. You cannot score 6.5 points. On the other hand, for a continuous variable, it can assume all values between any two given values of the variables. So the height of adult men. So you could say, well, this guy is 5 feet tall and the other guy is 6 feet tall. In between 5 feet and 6 feet, there's any any number, any arbitrary number of values. You can have 5.1, you could have 5.2, 5.3, and so forth. Well, that's if you want to do it in tenths. You could do it in hundredths as well. You could say, well, it's 5.11, 5.12, 5.13, and so forth. You could do it in thousandths of a foot, 5.111, 5.112, and so forth. So that's the concept here, is that continuous means it can have any degree of precision that you want. Now, many continuous variables, it just seems like this is the way the world is set up, have distributions that are bell-shaped. These are called approximately normally normally distributed variables. So the bell shape alone does not make it a normal distribution. What makes it a normal distribution includes some other constraints, some other criteria that we will discuss at the appropriate time. Okay, so here's an example. This kind of looks like a bell shape. This kind of looks like a bell shape. What's going on here is that as you increase the sample size and you get a smaller and smaller class width, what's going on here, it's getting closer and closer to being a nice smooth curve. Okay. And as he says here, there's no such thing as a perfect normal distribution. It's an approximation. A very famous quote is that all models are wrong, but many models are useful. And the idea is that you cannot perfectly model anything with a normal distribution. That's a theoretical distribution. However, we can make all kinds of inferences and we can make all kinds of rational decisions based on this model of a normal distribution. So we can describe things very, very, very well using this, okay? Okay, so this chapter, what it's all about is talking about the normal distribution. And we're going to learn all kinds of things that are very, very useful. I would say this is one of our better chapters, most useful chapter that we've got. That ultimately, we're also going to be using this for, I'm trying to, give me a second here, what we're also doing here is we're going to use the normal distribution as what we call an approximation to other distributions. For example, the so-called binomial distribution. The binomial distribution is difficult to calculate, as you know. I mean, it's a real pain in the neck, right? We can use the normal distribution to approximate the binomial distribution. And many times the approximation is good enough for the purposes that we intend to use it for. And it saves us an awful lot of difficulties. Okay, so that's the overview, that's the introduction. So this is recording number 1, and I guess that's about it.